Algebra 2 students, welcome to section 8.6, Common Logarithms. Common logs. So base 10 logarithms are called common logs. The expression log base 10 of x is usually written without the subscript as log x. So we have actually seen this before when using the calculator, just to kind of introduce the concept of a log. Really just typing in log x or log of a number is implied to have a base of 10. So we'll use the log key, as you know, on your calculator to evaluate common logs. Again, logs with base 10. The relation between exponents and logs gives the following identity: the inverse property of logs and exponents. So 10 raised to the log of x is equal to x. And the reason this is the case is because we actually have a base of 10 there. Okay? If we had a different base, and let's say, well, instead of a 10 here, let's say this was a 5, and let's say this right here was also a 5. If that were the case, then we'd still have x as an answer. It's the inverse property of logs and exponents that works in that manner, with those two numbers being identical. Evaluate log of 50 to the nearest 10,000th. Use the log key on your calculator to 4 decimal places, and when you do so, log of 50 is equal to 1.6990. So we have a base 10, so I'll ask that you type in this on your calculator, and when you do so, this is the answer that you'll get. I'm not able to use my graphing calculator here now, but if you go ahead and attempt that, you'll see that that's the case. Next example. Solve. 3 raised to the 2x plus 1 equals 12. So what we do is we look at the equation to start with, and using the property of equality of 4 logarithmic functions, what we're able to do is actually take the log of both sides of each equation, which is interesting because when you do so, in this case the log base 10, we don't see the base, but the base is 10, of 3 to the 2x plus 1, or I should say, you could do log base 3. But what they did here is use base 10. I'm going to do the same thing here, noting the base 10 on the other side. I'll talk later briefly about those two bases being not 10 necessarily, but in this case they are. And when you do that, what you're going to go ahead and do is move, just like we've done in the past with powers, move this up in front of the log, so it's 2x plus 1 times log 3, and that equals still log 12. I won't continue to write the base 10 because it's implied to be that base. If we continue, we divide both sides by log 3. We subtract 1 from both sides, then divide by 2. The math that we can go ahead and do here will result, if we take log 12 divided by log 3, this decimal divided by that minus 1, and then times a half. The calculator will yield the following decimal, 0.6309. Okay, so let's continue. So again, that answer was 0.6309. We can use our calculator to assess that value. We could also check the answer as well. If we move on here, it says use a calculator to evaluate each expression to the nearest 10,000th. So quite literally, all we're going to go ahead and do is type in log of 18 on our calculator. And if we do that, we'll get 1.25553. Now keep in mind, if you just hit the log button, this is implied to have a base of 10. So 1.2553. We can check the answer by taking 10, which maybe I'll write here as my base, raised to that power. And yes, 10 to that particular value is 18. Let's go ahead and do maybe 1 or 2 more here. Let's try number 3. Noticing here that again, we can write the base 10. So if we type in log of 120, the decimal ends up being 2.0792. And then if we check that answer, 10 to that power should end up being 120. Let's do one more. Let's do a number that's maybe smaller than 1. Number 6. So log base 10 again of 0.003. So 10 to what power is 0.003? Let's take the log of 0.003, and we'll end up with a negative 2.5229. 9. Now consider the fact that although we can't take the log of a negative nor 0, we can in fact get a negative result because 10 to that power, right, 10 to the negative 2.5229 power is really 1 over that. In this case, does in fact prove to be 0.003. Let's continue. Solve each equation or inequality. Now we're not going to be doing inequalities actually, so let's kind of cross that off, which also speaks to the fact that we'll not do 10 nor 12 or any problems following this that have inequalities. So number 7, we'll solve this equation and then round to the nearest 10,000th again. So if we look at this, and if you remember the example problem, they actually took the log of both sides of the equation. I'm not going to do that on this particular problem. Instead, I'm going to actually just simply rewrite it as a logarithmic equation. So log base 4, because that's the base on the left side, and because it's raised to the 3x power, it becomes that value or expression really on the right side, and you're actually taking the log base 4 of 12. If you work backwards, remember 4 to the 3x power equals 12, and that's exactly what we started with. So we can kind of check the setup by working backwards too. Now when it comes to solving this, what I'm going to go ahead and do is I'm going to use a formula. And the formula that I'm going to apply to this particular problem at this point, we haven't seen this yet. I'm going to go ahead and show you something called the change of base formula. Kind of previewing, so to speak, something we'll definitely learn in class later. Change of base formula looks like this. I'll rewrite the problem exactly as you see it, except on the left side, instead of a single log, it's actually 2 separate logs. And essentially what happens is we'll just simply using the base 10 for both. The numerator expression or thing that you're taking the log of is the 12, while the denominator is the 4 or the base. So individually, if we take the log of 12 and divide that individually by the log of 4, so 2 separate logs, we're going to get 1.7925, and that equals 3x still. Solving is pretty simple from here. We divide by 3, and then x ends up being roughly 0.5975. Alright, now that was a simple process, but as far as typing it in, but in terms of the actual formula in the application, which you haven't seen yet, I do like previewing certain things, in this case the change of base formula. Definitely something we're going to talk about later, but certainly it's not a bad time to take a look at it. I prefer this formula, frankly, over the example that is noted up above. Let's apply to number 8. So in number 8, we'll go ahead and do the same thing, rewriting the equation as such. So log base 6 of 18 equals x plus 2. So again, if I apply the change of base formula, we'll have the log of something divided by the log of something, and that still equals x plus 2. To go ahead and rewrite now, using the change of base, really the numerator is simply what initially I'm taking the log of, and divide that by the log of the base. So 2 separate logs as opposed to 1. So if we type this in, log of 18 separately, and then divide that by log of 6 separately, we'll end up with 1.6131. And that still equals x plus 2. Simply subtract 2 from both sides. We should have our answer. Should be a decimal that is rounded with a negative as well. Negative 0.3869. And that's our final answer for that problem. Now we can still check our answers. I didn't actually check 7 nor 8, but I can simply by plugging this in. So we'll say 6 to the, and I'll use parentheses, the answer negative 0.3869, or just use the answer button on my calculator. Add that to 2, close the parentheses, and it should be 18, and it is. And if we go ahead and move on, looking at some other problems here, we can see that there's a lot of similarities between 7, 8, 9, 11, and then problems that follow that are a little bit more complicated. We'll certainly be talking about those types of problems in class, particularly 14, 15, and 16, because all 3 of those are a little bit different and more challenging for sure. But really those others are certainly within your realm of understanding. So what I'd like you to do, on top of finishing up the 8-5 homework that the sub gave you, I'd like you to try on your own 9, 11, and 13. Use the change of base formula for those 3 problems, and go ahead and check your answer, measuring those against the answer key on OneNote that's already there for you. Have a great day, and we'll talk more tomorrow.